Hi, today we discuss set and map or dictionary data structures. So what is a set? Set can be considered as a magic bag where we can put billiard balls. So on billiard balls we have some numbers written on them. So for example, 8, so on. And if we put it to bag, so we firstly it is bag. It means that we don't have any order on elements in this bag. In one moment it can be one order, in another moment it can be another order. We don't uh, consider order on these elements. And second thing about this bag, it is magic, because if we have already ball with number 5, for example, and we want to put there one more ball with the same value that already exists in the bag, it disappeared. It means that in one moment in bag can be only one ball with the same value. So we put it here with 5, and uh, we still have only one ball with value 5 here, or another um, value like 8 or so. We can consider set not only set of integers, but set of strings, set of some class, and some another complex objects. Um, and But on this video, we will focus on integers, like most simple objects for considering. Okay, what we are interesting in when we consider a set. We're interested in 4 possible actions. First of them is adding an element, ball to bag. We checking existence of an element in the set. So we look to our bag and uh, looking for some ball with a specific value. Delete an element from set. So we remove ball from bag with a specific value and check the size of the set. So we check how many balls we have in the bag. If we consider, for example, Java, and set exists in many popular languages, if we consider, for example, Java, we can um, define set and define what the element of the set will be. So it is like what the type of values can be written on these balls in the back. And we can add element to set. We can check get true or false it contains element in set or not. We can remove element from set, some specific element X, and check size. So typically you have already implemented set in your languages, but the question is how to implement it yourself. So you should understand how it are, what is it inside these classes, these interfaces in your languages. So the first possible implementation is very simple. It is a list implementation. What we can do, we can have a list or just array of elements. The simplest is considering array of integer values. And what we do, if we want to add element, we have this. Okay, this array. We have a specific size of our set. So S is size of our set, and if we have S elements from 0 to S minus 1 are elements in our array, then we can add new element just writing element X inside S and increasing size to 1. Then if we want to check existence of an element, we just check all elements from 0 to S minus 1. And if the considering element is X, then we return true. Otherwise, in the end, we return false. So because it is magic bag, we cannot have two balls inside this bag with the same value. That's why when we add an element, firstly, we should find it and check maybe there already we already have element X inside our bag. That's why before adding element, firstly, you should check existence of an element. Then if there is no such element, that we add it in the end. So the similar for removing an element, deleting element, what we do, we firstly check existence of element X. If it exists and we find its position, that is J, then what we do, we just remove this J value from our array. We move all elements from right to left to one position, and that raising jth element and decreasing our size of our set to 1. Okay, so and finding size of the set, just returning this value s. Initially, for empty set, s is 0. The time complexity of such actions is O from S, because each action as add, removing, and also requires firstly check existence and finding this position, and existence requires O from S operations. And only size checking requires constant time, but all others O from S. But what about memory? If we implement it as an array, then memory is maximal possible size, that is 1000. If we implement it, for example, using linked list, then memory is like size of O from S, actual size of our list, but the simplest implementation is this one. Okay, such implementation is very slow. We have O from S complexity, and if S is big, then it is too much. Let us try to improve our implementation. We assume that all values that can be are from the range from 0 to 99. In that case, we can have something more efficient. So what we do, we consider a new Boolean array with 100 elements with indexes from 0 to 99, and it is something like characteristic vector, or it is array of indicators. We say that if AI is true, then the element I is in our set. And if AI is false, then it is not in our set. So in that case, how to add element? We just can put true to element of array with index x if we want to add x to our set. How to check existence of an element? We just check if AX is true or false. And how to remove element, we just put false to the. So here we can be sure that each element um, can be in our bag on only once. We cannot add two balls to our bag. So it is like if it is true, we assign true, it is still true, and it belongs to the set. If it was false, we assign false, nothing changed. If it was true, then we remove it. Everything okay. But for checking size, it is not so simple. We check all elements from 0 to 100, and if some element belongs to our set, if AI, sorry, here AI, because we check all elements from I from 0 to 99. If AI is uh, true, then we just increase our size and return. But at the same time, uh, here we have very fast implementation. It is constant. Here we have very fast implementation here also. But this computing set is not very fast implementation. Yeah. Um, so we uh, at the moment we keep it. Yeah, also I. Yeah, and in the case where we have not elements from 0 to 99, but from 0 to p minus 1, we can use array of size p and do the same. And when we check size until p minus 1. So in that case, we have O from P memory because we need this array. We have constant time for these three operations, but not constant time for the size. Okay, let us have the constant time for size too. How we can do it? So we can change the variable s when we add element or remove element from our set. So if s is always actual, then what we do, we just increase s if we add element. If the element x does not belong to the set and then we add it, then we increase it. So if it was false and it becomes true, then we increase size. If we remove and it belongs to our set, there is a ball with such value in our set and we remove it in fact. Yeah, if it was true, then we decrease size. And in that case, S is always actual and we can return this value. Initially, for empty set, S is 0 and all elements of this array is false. So we can decrease our time complexity for size S, get it constant, but we pay for it with additional memory. So here we should keep variable S as a field of our class, additional variable, and it allows us to have constant time for each operation. But this additional variable is not so big additional memory because we already have O from P memory complexity. But what happens if possible values range is too big. For example, we want to have set of longs, yeah, integers up to 10 to the 18. It can be set of strings or classes, and in that case, range is very big. And in that case, time is okay; it is constant, but memory is too much. It's unbelievable big memory. That's why we should do something with it.